Perfect.
Morning.
Good morning, everyone. Thanks for coming out early today.
Yeah. Happy Friday. Hope everybody's doing great this morning. We had a good rest. We have a lot of content for you guys today for 30 minutes, so stick with us. We're going to try to get through it, and I hope this helps.
And of course, we'll be staying late for questions in case anyone doesn't have a chance to ask the question before they kick us out for the next good presenter.
Disclaimers, you saw it, great, we're clear. Quick rundown of the agenda. We're going to introduce at least our definition of detection engineering. I think it's a little bit of a loose thing in this world right now. But then deep dive exactly to what this definition means to us, how do we apply it, right? The tools, process, and metrics behind it. And then we'll close it up with what did we all learn? And hopefully, again, you can walk away with something that's useful from this talk. So jumping right into it, wasting no time. How do you know your organization can detect attack X, right? Ransomware, gang, Y. Vulnerability, Z, right? And can you prove this in your environment? These are, I think, the core questions behind detection engineering. And to kind of take it a step further, can you answer this within 15 minutes of the question getting asked? This is exactly the premise of why. Yeah, like if you can't answer this within 15 minutes, you probably need a detection engineering in your life. So gather around our cyber campfire here. Thank you, AI-generated images. And I'm going to share you a quick little story. Hopefully it's 2 minutes long, and how we kind of bumped into this entire topic of detection engineering at Splunk Threat Research. A long time ago, about maybe 5-6 years ago, we started shipping detections to the Splunk Enterprise Security product, our SIEM. And the way we ship these detections were just searches. Hey, Mr. Customer, you want to solve a problem out of the box really quickly and fast? Here's a search, you can run it. Problem we ran into right away with shipping these detections where we started getting escalations from professional services. Probably don't want a bunch of those unless they're happy about the detections, which they weren't in this case. A lot of the escalations were like, hey, we try, our customers tried these detections. It just doesn't work, and we don't know why. Can you help us? Those escalations will take us between 3 to 2 weeks to answer. For a small team of threat researchers, that's a ton of work. I'm sure a lot of you live this today. I hope you don't. But this is how we bumped into detection engineering, honestly. It's trying to figure out how do we answer these questions faster, and how do we prove it to ourselves that this attack catches that threat, and explain it to our customers, our PS team, and the rest of the world in the most transparent way we can, right? So out of that exercise, I think our team, Threat Research, started building a bunch of tooling and efforts towards detection engineering. A little bit, 2 seconds on the team, Splunk Threat Research team. We specifically are the team that ships all the content for the Splunk product, so detection rules, playbooks, models, and all the engineering around that. We try to do a bunch of our work as public as possible, share with the community. Thank you so much, Eric.
Yep.
Yeah, so, and really our focus is we study threats, so what's the latest malware out there, what is it doing, reverse engineer it, write detections for it, or what's the latest emerging threat, CVE, figure out how it works, grab the POC, write detections for it. And then out of that comes a bunch of data sets. And Eric is going to show you a bunch of cool stuff we have from those data sets, but I'm excited to share that with you. And from those data sets, then we build detections off of that, right? We catalog these data sets, we curate them, and then we build detections that go into the Splunk SIEM for it. Part of this entire process is a bunch of tooling and tool chains that we use, which we also open source and share with you all. And finally, again, at the end of the day, the goal is for us to all get better, ideally fight back more effectively. So our intent is to be, again, as transparent as possible and share with the community so you guys can use the same tools yourself as well, hopefully. So, all that said, I asked ChatGPT, like we all do today, what is detection engineering? I got to write a talk, right? And it splattered this out. Actually a pretty good answer, not going to lie. But reading in between the lines, this is really, I think, what the core of detection engineering is, to me, at least, to us. It's a process. There's detections involved, which are sometimes rules, sometimes models, sometimes other things. This process is looking for malicious things, right? These detections are looking for malicious things. Again, I mentioned that there's rules, attack patterns, algorithms. Every environment is different. Every tool you have at disposal is going to work differently. But at the end of the day, you're developing, you're testing, and you're simulating attacks, TTPs, and detecting against them. And usually at the core of all of this all happens and it gets executed in a SIM, which is why we ran into it really, really fast as a company. So what are the core components of detection engineering, right? What are the things that you probably won't be able to do it if you don't have this, right? One is Git, or a Git workflow. Git, and again, Eric is going to get into it in a second, but it gives you a bunch of powerful tools under the hood to really manage detections at scale. So you can't really do this without a Git-driven workflow. Two, simulations. If you're not testing your detections, how do you even know they work? You sometimes don't have to simulate things necessarily. You may have customer data you can test them against, but simulations are probably the easiest way to make sure this detection works against that attack if you can simulate that attack to begin with, right? You need analytics. Can't detect something if you don't have an engine to detect it on. This is for us, of course, Splunk Enterprise Security, but there's a bunch of analytics engine out there. And analytics engine could be something as simple as a SQL server, by the way. So you know, finally, automation, right? It's great you detected something. Can you make it faster? So do some pre-built triaging of that process. How do we make this, essentially, how do we accelerate that SOC process to detect something and then answer it as fast as possible? I don't think the detection engineering lifecycle is complete without some automation behind it. And finally, how do you measure if you're actually being successful and making progress with detections? You need metrics, right? And metrics means a lot of things to different people also. And what kind of metrics you track changes from industry to industry, customers to customers. So, but as long as you have a measurement and a way to measure your success, I think that's kind of another core component of detection engineering. So, detection engineering has a set of components, but there's also a process behind it. And again, this is the way we see the process. Again, it may vary a little bit for you, but I think the general theme is here, right? You always start with an attack. Can't detect something you don't understand. And I see that a lot. Like sometimes, like, yeah, you know, yeah. Understanding what exactly is the threat, the TTP, and again, notice we're mentioning TTP a lot. Specifically, I'm referencing MITRE attack TTPs. But at the end of the day, you need something concrete you're going to go detect, right? A tool, a malware, an actor, whatever it is. And then you create a hypothesis. I think I can detect this ransomware when it writes a bunch of files to disk. So that's my hypothesis. I think I can detect this remote code execution when it comes across the wire in my web logs, right? Once you have a hypothesis, the next immediate step is making that happen, right? Making that attack happen in your environment in some simulated way. Or ideally, if you're lucky, you find it in, or unlucky, I guess, you find it in your customer's environment or your own logs, unfortunately, and now you have data for it. But the whole point of this entire thing is get data for that attack, right? See how it actually looks under the hood, right? It's one thing is reading it off of a threat report. Another thing is actually seeing the logs yourself, seeing the data yourself, seeing the attack come across the wire, getting it running. And finally, once you have that data in the process, you can now create a detection. Otherwise, without a threat, a concrete threat, without some data behind it, you're going to have a rough time writing a detection. And sometimes writing a detection really means I can use something existing. I hope most of you know about the Sigma project, Sigma HQ, amazing community effort. They give a bunch of detections out for free for the rest of the world. So use 16 detections or create your own. But immediately, I think the next step after that is testing that detection. And again, that's where that attack data set, that simulation comes into play. Put it in your SIM, rerun that attack. Does the detection actually trigger? If you have a POC, rerun that POC in a localized environment. Does it actually trigger? Now we've completed essentially the detection engineering process. Now we have a working detection. We can trust and we can answer within minutes how it works, why it works, and essentially show it, right? Be transparent about it. And there's a final piece in there. I think it's missed out by a bunch of folks when we talk about detection engineering, but you need to deploy this thing. So how do we package it in a way that is usable in an environment, right? Again, for us in Splunk, this means a Splunk app. Enterprise security content updates. We ship it to the product. It gets updated every 2 weeks. You get new detections every 2 weeks. It changes from product to product. It changes from environment to environment. But packaging is actually sometimes one of the most difficult pieces of detection engineering, believe it or not, especially for researchers that don't control the environment they're developing detections on or they're deploying to. So don't miss on that last process step. It's important to think about how you're going to package it, how fast you can deliver detection. Sometimes you need to block an emerging threat within hours, not days, and that sometimes is the hang-up. It's not the entire other piece of the process.
All right, thanks, Jose. So now that we have an idea about what that detection engineering process looks like end to end, let's actually talk about some of the specific tools or ideas or methodologies that we use to actually implement it at Splunk. We will call out some very specific tools that we use that are open source, that we've either developed and shared with the community, or that the community has developed, but it's really the process as a whole. So just keep in mind that we're more concerned with the process and we're not going to get bogged down in some very specific tool or subset of tools. So let's talk a little bit about the importance of tooling first. So let's just go with some of the most common questions that come up when you're looking at a detection. So the first one is, what the heck is this detection supposed to do? Well, maybe it's documented somewhere in a Jira ticket, some emails, some Post-it notes, the guy's brain that left 6 months ago. So how am I supposed to find out what this thing's supposed to do? Second, this detection seems to work in one environment, but not another environment. Well, what's different about those environments? Is it documented somewhere, or do you have to do some in-depth investigation into those environments and then figure out yourself what's different about them? Third, hey, there's new upgrades available for my platform for these applications. I'd like to upgrade them because the newest release is always more secure, it's better, it's more stable, it's got more features, but what if it breaks my detections? How do I even know if it breaks my detections? No one wants to go and test all that stuff by hand, so people don't update as frequently as they should. And then finally, this thing used to work, who's the person that changed it? And ultimately, after some soul searching, we usually find out we're the ones that changed it. So if we had some processes that could help us do this automatically, all these things just become easy and they're done for us. So instead of documentation across separate systems, we have inline documentation. We'll actually show some examples of that inline documentation today. Instead of figuring out why this works in one environment and not other ones, we can actually have configurations of different environments that do that testing for us automatically. In terms of choosing what I can and what I can't upgrade, well, if you have those different environments, you can atomically upgrade one version of one specific piece of software, see if something breaks, see if it doesn't break. And after you've done that testing, you have confidence that you could deploy that into production. And that's where I start to talk about one of our first tools that our team has built that's open source called Splunk Attack Range. And this is actually Splunk's most popular open source project. You can just grab it at github.com/Splunk/attack range. What you see up here is exactly what Attack Range sets up for you in about 10 minutes after you've cloned this repo. Those individual boxes are all different pre-configured virtual machines for you. So in about 10 minutes, you run, no exaggeration, 4 commands, and then either locally or on AWS, you have a full virtual machine-based attack range set up for you with Windows installed on it, with some Linux endpoints, optionally with Kali Linux for simulation, and then even a pre-configured Splunk server, by the way, ingesting in a proper configuration all those data sources from all those endpoints that you've stood up. But wait, there's more. We actually include some simulation frameworks, most notably Atomic Red Team, that we'll talk about in a little bit more detail, to actually run attack simulations. So really, really easy way to generate the test data that's going to be so important later in the presentation and to the whole detection lifecycle. And then in terms of, hey, who changed this thing? It used to work. We really double down on version control systems, which we'll talk about in detail. So not only is your documentation in line with your content, but the history of that content is in line with that content as well. This is just an example of commit messages that many of you might have seen for version control systems. I'll talk a lot about GitHub, because again, it's one of the most popular sources and really easy to use. But not only do you get those commit messages, but you get the ability to run automated CI/CD or continuous integration, continuous deployment jobs on every single commit or every single change to your content. So that's something that we're going to leverage a lot in the workflow that we're talking about as well. So we don't have to build all these things from scratch. the DevOps and research communities have actually done a lot of it for us. So the first question is, how are we going to store our content? And we've already made the strong case for the usefulness of a version control system to get all the history of that. Obviously, there's lots of choices, lots of different Git providers, other version control systems. The second question is, how are we going to perform some validation or quality assessment of the content in a very, very quick way? So how do I ensure that my detections include specific fields, specific enrichments like detections, maybe unique IDs, maybe test data sets, those types of things that are ultimately going to be really important when I'm running this in product. The next question is lab environment, which we touched on a little bit before. Jose said simulation is so important. I've talked about simulation as well. I'm going to talk about it 3 or 4 more times during the talk because it's really, really important, not just for learning yourself, for personal education, but actually proving the hypothesis of the signatures that I believe that this malicious behavior is going to create, and not just that they create them in some environment, but that they create them in a very specific environment that's properly configured so that I can actually ingest them and process them. So finally, a lot of these decisions for specific implementations are going to be driven by what SIM or what other technology you're trying to deploy them into. So ultimately, we typically develop with Splunk Enterprise, Splunk Cloud, et cetera, as our targets. But really, you should use this to inform your final choice as to whether or not there's good integrations for your target SIM to work with some specific open source or commercial tooling. Next, let's talk about the actual process that we go through now that we've identified some of those technologies. So how do we tie those different tools together to actually develop something that works at the end of the day? So we all know that change happens all the time in the world. It certainly happens in our industry. It's expected. We don't expect things to stay the same. Obviously, the technologies evolve. And it's also really critical to address those changes so that we know that whatever content that we've built, whatever tooling that we've built is up to date and still works in the environments that it's deployed into. So the positive about change is obviously that it can fix errors or oversights that we had in the past, maybe things that we weren't aware of, maybe things that we become aware of. But the other issue is that it can break things that were previously working. So some automated tooling that helps us assess whether or not something's working better today than it was yesterday is extremely important. And as I mentioned before, this is the second or third time I'll mention version control. Being able to track the individual changes to individual pieces of content or files is really important, but also collecting high-level metrics such as 97% of my detections were passing a week ago, and today 85% of my detections are passing. Let me look at that set of changes that took place in my environment and that set of changes that took place into my content so I can start to learn, hey, what happened over the past 2 weeks to degrade or likewise improve the quality of all my content in my specific environment over the past 2 weeks. And having that insight is really invaluable. In terms of simulation, this isn't something that's unique to the cybersecurity industry. You can see simulation is really important across a lot of different industries. So I'll ask everyone, how are you supposed to defend against something that you haven't seen in your network yet? You don't have test data for. Maybe you just have a CVE announcement. Simulation is critical not just for our industry, but a lot of industries where time is important and the cost of failure is so high. Doctors and nurses and hospital staff practice on standardized patients in a lower stress environment. Pilots, of course, have flight simulators. The military has war games. Every time you go to sports practice, you're practicing plays in a lower stress environment. And even physical security has penetration tests, which is maybe one of the closest analogs to the cybersecurity domain. So again, I posit the question, why should a high-stakes, high-pressure environment like cybersecurity be any different than any of these environments? In terms of some of the specific implementations that we use to perform simulations, one of the most important things is a large set of simulations that we can run out of the box. So there's a lot of different simulation providers. One of our favorites that we're actually a really big contributor to is a project called Atomic Red Team by a company called Red Canary. And what's really great about this is a set of, at this point, thousands of very small simulations that they call atomics, which are, again, available on GitHub, which are just a series of commands that are tagged with very specific descriptions and MITRE ATT&CK IDs. So if you notice a couple slides ago, we were running a Python attack range command, and we gave the MITRE ATT&CK ID of an atomic with the simulation engine Atomic Red Team. we're actually pulling down that repository, running the atomic, which could be a PowerShell command, it could be executing an executable, installing a DLL, a bunch of shell commands to exercise those things in a very particular way. And then we do that on a test infrastructure so that we can collect logs from that test infrastructure. Specifically, the test infrastructure we use most commonly, again, is called Attack Range. Fully open source, configured out of the box to work and ingest almost all of the logs you could want directly into a Splunk server. But guess what? It's actually configured with a bunch of Ansible scripts. It's all open source. So if you wanted to put some custom software on there, do some custom configurations so that it more closely mirrors your production environment. If you want to actually install another XDR or endpoint logging provider that we don't install today, really, really easy to do, just as simple as updating some Ansible scripts. So now we have a way to simulate specific attacks that have already been tagged and annotated for us. We have a place on which to run those attacks. And we do all those attacks so that we can generate some test data. Of course, you can generate all this test data yourself, but we believe in giving back to the community. So we actually take all these attacks, we tag them with the log source they came from, we tag them with the MITRE ATT&CK ID that they're representative of, and then we update them to this curated repository called Splunk Attack Data, so that if you just wanted to download some data that was representative of an attack, without having to do steps 1, 2, and 3, you could just download that and replay that into your own environment. Could be Splunk, could be another endpoint, because these are actually raw logs. Ultimately, we'll also use this test data to power our automated testing system I'll talk about in just a few slides. So the next component that I want to touch on in a little bit more detail is that content is so much more than just a search or just a detection. In Splunk parlance, that means that a detection is more than just the SPL that executes on your search head. It's the description, it's the name, it's all the resources, the blog posts that went into actually understanding and crafting that underlying attack. And then for Splunk specific aspects, it might be things like risk-based alerting and risk scores, even SOAR playbooks or other things that you want to connect to. And all of this information is really important, not just to you in building the detection today, but to the next person that's going to look at it that might not have all the knowledge that you have when you're originally writing the detection. So not only is this good for us as we update the detections that we wrote, but it's really good for our coworkers and colleagues who might be looking at what we've built. And it's really, really good if we share this back to the community, because we provide evidence that we actually did our work and our research to build a high quality detection. So all of those ingredients go into this nice gourmet meal detection that we have here. But the issue is there's a lot of work and there's a lot of mess that gets created when you're building something that nice. So of course you use a lot of tools, make a little bit of a mess, and those tools are kind of purpose-built. Kind of the first tool that you might use that we mentioned before is something that just provides some high-level validation. So have you included all those fields that you might call required, and do those fields have values that make sense and seem reasonable? So is that risk score a number? Do those reference links link to real websites that have descriptions on them? Is your SPL valid, or does it contain invalid characters, et cetera, et cetera? So once you've done all those initial checks, which by the way, fail and should fail really, really fast in a matter of seconds and give you immediately actionable feedback so that you can very quickly iterate on your content, let's actually build something that we could deploy in our production environment. In our case, this is either a JSON object or a Splunk app, but having that happen in an automated way is much better than having it happen in a manual way. The next step, once we've done that linting and building step, is to actually test this. And in our case, we take that app that we've built previously, which again is built up of, at this point, over 1,000 detections. We'll configure our environment, we'll replay that test data that we generated during our simulation step, and then we'll actually execute our searches to make sure, one, that they actually run and don't have any syntactical errors, and then two, they actually find the results that we intend them to find. And specifically, the tool that we use to do this is another open source tool called ContentCTL. We're really proud that we just released version 4.0 3 days ago, so I encourage everyone to take a moment and check out that tool and the documentation for that tool when you have a chance. Finally, once we've built our content, we've built our simulations, we have the results of all our tests, let's compile all that stuff into actionable metrics that we talked about a little earlier in our conversation today. One of the biggest metrics that are really useful at the high level, so CISO, SOC manager level, might be just a simple coverage diagram. And the way that we generate this is that we annotate all of our attacks with test data, and we actually annotate them with the MITRE attack IDs that they're meant to detect and cover. We do lots of other annotations too, like specific CVEs that might be useful in very specific use cases. But something like this is extremely useful if you just want a view from 1,000 feet level of what your coverage looks like, and also what areas you're not covering well. The second thing that we do is we look at our coverage across specific asset types. So do I have a sufficient number of cloud detections across a number of different cloud providers? What types of endpoints am I covering well or not covering well? And also, am I even bringing in the right types of logs that are representative of those endpoints? Same questions for specific applications that you may be collecting logs from, and then specific pieces of network gear, for example, that you might be bringing in. So being able to just have these at a view from 1,000 feet is really, really useful to see where you're doing well and then where you need to improve from. And then as you track these over time, because again, you have this automated system for validation, building, and then ultimately testing the performance of your content, you can start to see, are we improving? Are we getting worse? Are we staying the same? And then specifically, where do we need to improve in the future? So all of these metrics are really useful at a high level, but really useful to an individual detection engineer or detection author as well, so that you can start to actually budget your time to fill in those gaps instead of kind of defaulting to your favorite thing to work on, or maybe even the thing that you're most comfortable working on. So once we've collected all these metrics, once we've built our app, once we've tested it, we actually need to get it into production somewhere. And as Jose mentioned, this is often the thing that people forget after they've done all this hard work in the beginning. So again, this is really SIEM dependent. How do I actually want to get this into production? And one of the big questions is, do you really want to double down on that DevOps approach of, hey, if this passes my tests in CI/CD, I want to deploy it automatically? What's great about that is it reduces your time to actually get that into production by a significant order of magnitude. But alternatively, if you don't have as much trust in your CI/CD systems, do you really want that human-in-the-loop review before it actually goes into your production environment? So make sure you're aware of the different ways of moving that item into production, be it installing by hand, be it deploying via API, or something along those lines. Finally, something that's often also glossed over is the actual tuning and then maintenance and full life cycle of that content. So your environment's changing, the underlying logs are changing, the actual threats are changing. So how do we keep pace with that? Always make sure that you're listening to analyst feedback. That's both the explicit feedback, for example, when they label something as a true positive, as a false positive, and it's the less explicit or more implicit feedback. So do people actually enable your detections? Do they open trouble tickets? Do they come to you and either complain or at the same time tell you something's really, really high quality? So they're the ones that are looking at the products of your work. Make sure you listen to their feedback. The second thing, of course, is test results. We've actually talked about that at length. We always want to quantify why something has gotten better, or similarly, why something has gotten worse. And keep in mind, test results or your pass rate or something along those lines going down might not necessarily be a bad thing, because if you introduce extra checks into your pipeline that actually make your testing more robust, it might uncover failures that you weren't aware of before. So don't necessarily get caught up on a specific percentage or number. Try and quantify that number in the context of the types of checks that you're doing. Third, of course, we always want to keep pace with evolving data and threats. So that test data that you've generated, those test environments that you're running in, might actually be getting stale. So make sure that at times you're retesting detections in a new, fresh environment. Make sure you're running with the latest versions of apps, latest versions of TAs, even latest baselines of operating systems or your SIEM platform itself. And if you do all these things, you'll actually start to build confidence in the individual pieces of content that you're building. You'll also start to build confidence in the content from the perspective that your analysts are actually consuming it. And you'll start to build higher level confidence as you provide metrics to SOC managers and CISOs. And of course, your customers will start to see the impacts of your increased security as well.
So that was a lot of data. Thank you for sticking with us. What did we learn today? Before I jump into what we learned today, though, I want to mention two key things. One, Everything Eric shared, specifically the tools, are all free and open source. Like I mentioned earlier, we want to be as transparent as we can be with how we do our work. Two, remember I mentioned earlier, it used to take us like between 3 days to 2 weeks to answer what attack we mitigated and how does it work. We're down now to minutes, usually. Like go search it up in a site that we have that already documents a bunch of stuff. So following a process for detection engineering does work. There's a lot of toil in it, but it will reduce and it will answer the questions that I asked at the beginning of the talk. So what do we learn? Quickly, this whole thing is there's a maturity cycle here, right? Don't expect, especially if you're not applying detection engineering methodologies or you don't have some of these components implemented, to be doing this out of the gate. We started, this was our maturity cycle. We started with an ad hoc process using Jira's, Excels, et cetera, to track what we were working on. We were testing things in production, which is not ideal. And a lot of it was emergency based. Oh, we need a detection for this threat. Let's go do it. Right? We weren't even getting ahead of some of the threats we wanted to cover. The next kind of phase in our maturity process was we started building a process around how we would intake cases that we were going to deal with. We started building a deployment process. Again, going back, that's one of the things that was really hard for us at Splunk. Because, okay, how do we get these detections out the door fast? Not in like 2 weeks, within 24 hours, right? But we still were doing a bunch of manual testing for quite a while. I think we didn't really have automation in testing for at least a year and into this whole detection engineering thing. After we had a process, we realized, oh man, we can make this process a lot faster and more efficient if we had all these tools, which is where you see a bunch of tools like attack range, attack data, so on and content CTO came about, and we started writing. And then we started using Git exclusively almost for managing all of our detection content. Then we jumped into automation. Once we had a bunch of these tools built, we were still running them manually, and we had a process that we were following, but it would still take us multiple days to get a release out because we're running them manually. Feedback was not distributed throughout the team. But then we started adopting a lot of CI/CD methodologies and started baking the execution of these tools into our development process for these detections, and then enforcing a lot of the things that we would ad hoc check as code. So like a developer immediately knew, hey, your detection's broken here, here, here. Go fix it. And you don't have to go wait for like a release to learn that, right? And then the final thing that I think we're still trying to get good at, we're honestly not perfect, but we're walking in that direction, is how do we make this continuous, right? How do we measure the efficacy of our detections, how well they're performing, how do we expand our coverage intently that helps our customer? And we're still reacting, like this entire industry is, to a lot of threats, but we're reacting a lot faster. We're adapting to these threats a lot faster. And I think in many cases, this is the best we can do as defenders. And again, this entire process helps us do this better, right? And measure the fact that we're doing this better. This is a wall of text. We just wanted to throw it up there with all the resources. Again, we've built essentially for ourselves that we shared out as open source projects with a little bit of what they do, what the action is, and then the link on how you can get them and read more about it. But again, utilize them to your will. They're all free. And I think, Eric, this is the section we start doing the Macarena interpretive dance for.
I think so.
No, seriously, thank you so much for coming. We really appreciate you listening to us. I think we have one more slide. And this is a bunch of folks jumping out of an airplane. Never going to do that. But if you do jump out of the airplane, please try doing detection engineering. If you have any questions and you can't stick around to ask us the questions, that's our team email. So everybody gets it. research@splunk.com. And thank you for coming. Happy Friday again.